So next we will discuss the convolution property of Laplace transform. Okay, it's a very important property, but we will discuss in later when you discuss the transfer function of an LTI system. Okay, and we will also discuss two questions related to this. So this is a convolution property. If there is a signal x1 of t and the transform is x1 of s, and the ROC of that particular signal is represented by R1. And there is another signal x2 of t and the transform of the signal x2 of s, and the ROC of that particular signal is represented by R2. And if there is a signal is in the form x1 of t convolution x2 of t, then its transform is very simple, x1 of s into x2 of s. So very important property. Mainly we will use the analysis of LTI system by using this property. Okay, LTI system analysis, we will use this convolution property. Okay, and about the ROC, is actually the intersection of R1 and R2. Okay, but we can say that at least R1 and R2, intersection of R1 and R2 means sometimes the pole zero cancel occurs. At that time the ROC will be greater than R1 intersection R2. Okay, that's why I use this word at least R1 intersection R2, and some cases it will be greater than R1 intersection R2, more than that. Okay, that depends on the particular question. Okay, when there is a pole zero cancellation occurs. Okay, when there is a pole zero cancellation occurs, so at that time the ROC will be more than this R1 intersection R2. Okay, and now we will discuss a question. Find the Laplace transform of the signal which is given e raised to minus 2t into u of t convolution e raised to minus 3t into u of t. Okay, and assume that this is a signal. For example, this is a signal x of t. Okay, e raised to minus 2t u of t convolution e raised to minus 3t into u of t. Okay, basically a convolution operation, for example two signals x1 of t convolution x2 of t, if you write the equation in time domain, it becomes integral minus infinity to infinity x1 of tau into x2 of t minus tau dt. That's equation. Okay, and first we need to calculate convolution by using this particular formula, and then we need to apply the Laplace transform. So in place of x of t, so without using the property, if you approach this particular problem, you need to find out Laplace transform like this. X of s integral minus infinity to infinity, in place of x of t. Okay, in place of x of t you need to write this equation. Okay, means you need to write e raised to minus 2 tau into u of tau into e raised to minus 3 into t minus tau into u of t minus tau, and integration is from minus infinity to infinity d tau. Okay, into the remaining portion, that is e raised to minus st. Okay, this is the usual way. Without using property you need to approach. Here you can see that there is two integration. One is with the variable tau and another one is with the variable t. Okay, this complex operation becomes very simple if you know the sorry, I made a mistake. This is not differentiation in S domain property, it's actually the convolution property. Okay, so this is a convolution property. Okay, by using the convolution property, we don't want to expand like this. Okay, simply you can write, if you know the transform of x1 of t and x2 of t, the convolution transform, simply you can write x1 of s into x2 of s. Okay, so we will approach the property method. So by using the property is very simple. So this is without using property. Okay, without property. This is a direct method. Okay, it's very complex, so we will not prefer that particular method. So we will use the convolution property. So e raised to minus 2t into u of t. The transform of that particular signal is 1 by s plus 2, and the ROC is sigma greater than minus 2. And another signal is e raised to minus 3t into u of t. And the convolution, Laplace transform of that particular signal is as 1 by s plus 3 and sigma greater than minus 3. And now we need to find the Laplace transform of the signal e raised to minus 2t into u of t convolution. It's not multiplication, it's convolution, e raised to minus 3t into u of t, okay, which is given by simply the product of these two. So 1 by s plus 2 into 1 by s plus 3. See, here it is multiplication, here it is a convolution operation. So here it is convolution, here it is multiplication. And the ROC you can write sigma greater than minus 2 and sigma greater than minus 3. Okay, so the intersection. So if you take this is sigma axis, this is j omega axis. One signal is minus 3 here, here it is minus 2. So one signal exists from minus 2 greater than minus 2, okay, towards right. Okay, second signal is exists from minus 3 onwards, okay, greater than minus 3. But both signal converge for sigma greater than minus 2. Okay, from minus 2 onwards both signal converge, so you can write sigma greater than minus 2. So that is ROC. Okay, okay, it's a very important property, the convolution operation in time domain. Okay, convolution operation in time domain becomes multiplication in S domain. Okay, it's a very important point. This is one of the advantage of using transform. Okay, so you need to remember this point, convolution in time domain because multiplication in S domain or in frequency domain. Okay, it's a very important point, you should remember. Another point we will discuss here, it is find the transfer function of an LTI system. Okay, LTI system means a system which obey linearity property and time invariant property. Assume that the input of the signal is x of t and the output of the signal is y of t. Okay, and the impulse response is represented by h of t. And we know that for the convolution signal, this y of t can be written as x of t convolution h of t. So which can be written as integral minus infinity to infinity x of tau into h of t minus tau. So that is the definition of convolution integral. Okay, so this convolution integral, by using this convolution integral we can find the output of a system in time domain. So this is the input of the system, so this is the impulse response, response of the system. Now we need to find the transfer function. Transfer function means actually y of s by x of s. Okay, that is known as a transfer function. So also represent as h of s. Okay, this is a transfer function or we can say that h of s is the Laplace transform of h of t. Okay, the Laplace transform of impulse response is known as transfer function. So Laplace transform of impulse response is known as transfer function or h of s, and x of s is the transform of x of t and y of s is the transform of y of t. Okay, so by applying the convolution property, so here it is a convolution property, I can mark this particular equation. Okay, so this particular equation, okay, y of t is equal to x of t convolution h of t. I'll write this equation: y of t is equal to x of t convolution h of t. So I'll take the Laplace transform of this particular equation. So it becomes transform of y of t is y of s, and transform of x of t is x of s, and the convolution operation becomes multiplication, and the transform of h of t is h of s. So now we can rearrange the equation, and you can write h of s is equal to y of s by x of s. Okay, so this is a transfer function. It's a very important property. You can see that in time domain we cannot write like this: y of t by x of t, which is not equal to h of t. We cannot write like this. Okay, this is completely wrong, because this operation is convolution operation. But in S domain we can write like this: h of s is equal to y of s by x of s. Okay, so don't do this operation in time domain, multiplication operation. We are performing in S domain. Okay, so this equation is very useful, and if you calculate the inverse of inverse Laplace transform of h of s, you will get impulse response. Okay, in this way also we can calculate h of t. So very important point: the Laplace transform of y of s by x of s is known as h of s, which is known as a transfer function. Okay, thank you.